Welcome back to Fun Facts Online. Today we are not talking about a small update or a minor gadget release. We are talking about a moment in history that might eventually be ranked alongside the first flight of the Wright brothers or the invention of the transistor. We are talking about the end of the noise. Specifically, we are going deep into the architecture, the physics, and the staggering implications of Google Quantum AI's new processor Willow. If you follow technology, you have heard the buzzwords: quantum supremacy, qubits, entanglement. But for the last 30 years, there has been a dark cloud hanging over the entire field. A mathematical paradox that suggested we might never actually build a useful quantum computer. That paradox was the problem of noise. And in December 2025, inside a super-cooled laboratory in Santa Barbara, that paradox was solved. Today we are going to break down exactly how they did it, looking at the 105-qubit architecture, the tunable couplers, the role of DeepMind, and a number so large it makes the age of the universe look like a rounding error. Let us dive in. To really understand why Willow is such a big deal, we have to start with the fundamental tragedy of quantum mechanics. In a classical computer, like the one you are using to listen to this, the basic unit of information is a bit. A bit is robust. It is a switch. It is either on or off, 1 or 0. You can heat it up, you can shake it, and it stays a 1 or a 0. But a qubit, the quantum version of a bit, is different. It exists in a superposition, a complex mix of 0 and 1 simultaneously. This state is incredibly powerful, allowing for massive parallel computation, but it is also hypersensitive. It is allergic to the universe. A stray photon of light, a tiny vibration, or a fluctuation in temperature can cause the qubit to decohere. When it decoheres, the magic smoke gets let out. The quantum state collapses, and you get an error. For decades, this created a trap. To do useful calculations, we need a lot of qubits. We need thousands or millions of them. But every time we added a new qubit to a chip, we added a new source of noise. It was a game of diminishing returns. The bigger we built the machines, the more fragile they became. It was like trying to build a house of cards where every card you added made the wind blow harder. This is where the concept of quantum error correction comes in. The idea, proposed back in the 90s, was to stop relying on individual fragile physical qubits. Instead, you group them together. Imagine a choir. If one singer forgets the lyrics, which is a physical error, the voices of the other singers drown them out, and the song continues correctly. The group of singers forms one logical qubit. In a quantum processor, we arrange physical qubits in a lattice, like a checkerboard. They constantly check their neighbors for errors, without actually looking at the data itself. But here is the catch, and this is the part that has kept physicists awake at night for 30 years. The act of checking for errors requires hardware. It requires gates and wires. And those things introduce noise too. So if your hardware is not good enough, adding more qubits to the choir just makes the noise louder. This is called the threshold theorem. It posits that there is a specific quality line. If you are above the threshold, getting bigger makes things worse. But if you can get your hardware below the threshold, magic happens. Adding more qubits cleans the signal. The error rate drops exponentially. This is the headline. Willow is the first chip in human history to cross that line. Google proved this by encoding logical qubits using something called a surface code. When they used a small grid of qubits, a distance 3 code, they got a certain error rate. When they scaled up to a larger grid, a DISTANCE5 code, the error rate dropped. And when they went even bigger, to a DISTANCE7 code, the error rate dropped again by a factor of 2. This is the first time we have ever seen a quantum system where making it larger made it better. It proves that if we keep building bigger chips with this architecture, we can drive errors down to 0. So how did they actually build this machine? Let us look under the hood of Willow. This is not just theoretical physics, it is extreme engineering. Willow features 105 superconducting transmon qubits. A transmon qubit is essentially an artificial atom made from circuits of niobium and aluminum. These circuits are cooled to 20 millikelvin, that is colder than the vacuum of deep space. At these temperatures, the metal becomes a superconductor, allowing electrons to flow with 0 resistance. But the number of qubits, 105, is not the most important stat here. It is the quality. The defining metric for a qubit is its T1 coherence time. This is how long it can hold information before it decays. On the previous generation chip, Sycamore, the coherence time was about 20 microseconds. On Willow, it is 100 microseconds. That is a 5-fold increase in the lifetime of the quantum state. This extra time is critical because it gives the control electronics enough time to spot errors and correct them before the whole system falls apart. But high coherence time alone is not enough. You also need to control how the qubits talk to each other. This brings us to one of Google's secret weapons, the tunable coupler. In many quantum chips, qubits are statically connected to their neighbors. It is like living in an apartment complex with paper-thin walls. If you talk to one qubit, its neighbor hears you. This is called crosstalk, and it is a major source of errors. Willow uses tunable couplers that act like adjustable valves between the qubits. The system can turn these valves off completely to isolate a qubit, or turn them on to entangle it with a neighbor. This dynamic architecture allows for incredibly precise control, reducing those parasitic errors that plagued earlier generations. However, having great hardware is useless if you do not know an error is happening. Error correction is also a software problem. As the chip runs, it generates a massive flood of syndrome data. These are measurements that hint at where errors might be hiding. To handle this, Willow is paired with a real-time decoder developed by Google DeepMind. We are seeing the convergence of two massive technologies here: quantum computing and artificial intelligence. The AI analyzes the syndrome data on the fly, identifying the ghosts in the machine and telling the control system how to fix them in real time. Now, let us talk about raw power. To prove Willow works, Google reran the random circuit sampling benchmark. This is a highly complex mathematical problem, designed to be easy for a quantum computer, but a nightmare for a classical one. In 2019, the Sycamore chip did a calculation in 200 seconds that would have taken a supercomputer years, but there was always some debate about those numbers. With Willow, the debate is over. Willow executed the benchmark in under 5 minutes. Google estimates that Frontier, which is currently the fastest supercomputer in the world, an exascale machine capable of a billion calculations per second, would take 10 septillion years to match that result. Let us pause and visualize 10 septillion years. That is a 1 followed by 25 zeros. The universe is only about 13.8 billion years old. You could run the simulation on the world's fastest supercomputer for the entire age of the universe, then restart it and do that a billion times over, and you would still not be finished. Willow did it in 5 minutes. This result is what we call quantum supremacy, or quantum advantage. It proves that we have officially moved beyond the ability of silicon chips to simulate quantum systems. The gap is no longer linear. It is exponential and unbridgeable. So why does this matter to you? Why does this matter to the global economy? The first major implication is the end of approximation and the beginning of discovery. Right now, when we design a new battery or a drug, we use classical computers to guess how molecules behave. But molecules are quantum mechanical objects. Classical computers are terrible at simulating them because the math gets too big too fast. With Willow-class error correction, we are on the path to fault-tolerant quantum computing. A fault-tolerant machine will be able to exactly simulate the chemical bonds in a new battery cathode or the protein folding of a virus. Think about energy. We could design room-temperature superconductors or ultra-efficient solar cells that we currently cannot even model. Think about medicine. We could simulate how a drug interacts with a specific protein in the human body, slashing the time for drug discovery from years to weeks. We are talking about materials science revolutions that could change aerospace and construction. This is not just faster computing, it is a new kind of science. Then, there is the issue of security. You have probably heard of the threat quantum computers pose to encryption. Willow itself cannot break RSA encryption, which protects your credit cards and emails. It is still too small. Breaking standard encryption requires millions of physical qubits to create the thousands of logical qubits needed for Shor's algorithm. However, Willow proves that the physics required to build such a machine actually works. The timeline for Q-Day, the day quantum computers break current encryption, has shifted from a vague possibility to a concrete engineering roadmap. Google says we are likely 10 years away from that scale, but for governments and security agencies, the threat is immediate because of the store now, decrypt later strategy. Bad actors can harvest encrypted data today and wait for the hardware to catch up. This announcement effectively lights a fire under the global migration to post-quantum cryptography standards. Finally, Willow highlights a new economic reality. This is not a technology that can be built in a garage. Constructing Willow required a dedicated superconducting fabrication facility, dilution refrigerators that get colder than space, deep integration with DeepMind AI, and billions of dollars in capital. This consolidates the power of quantum computing into the hands of a very few major players. We are seeing a new economic moat being dug around high-performance computing. So what comes next? According to Julian Kelly, the director of quantum hardware at Google, the roadmap is now focused on scaling logical qubits. They need to move from 105 physical qubits to 1,000, then 10,000, and eventually 1,000,000. They need to demonstrate logical memory that lives effectively forever and perform calculations between logical qubits. This is the transition from the Willow era to what comes next, potentially a chip class they might call Maple or Oak. Google has also opened access to Willow for researchers at the UK National Quantum Computing Centre. This is critical because writing code for a logical quantum computer is fundamentally different from the hacks we use today. We need a new generation of computer scientists who think in quantum logic. To wrap up, December 2025 will be remembered as a turning point. Before Willow, quantum error correction was a beautiful theory scribbled on whiteboards. It was a hope that nature would cooperate. With Willow, the theory has become metal, silicon, and microwave pulses. we have proven that we can tame the chaos of the quantum world. The noise has not been silenced, but for the first time in history, we have learned to speak louder than it. The quantum age is no longer coming. It is here. Thanks for listening to Fun Facts Online, and we will catch you in the next deep dive.